Hello, my name is Shim from Chung University, Korea, and here are my co-authors, graduate students. And I'm currently doing a research project on smart construction. So among the project outcomes, I will introduce DFMA for prefab bridges using data engineering models. I'm very happy to have presentation in this virtual ABC conference. These are contents of my presentation. As you see in this slide, the Smart Construction Research Program in Korea consists of 4 major areas and 12 sub-projects. And I'm in charge of second area, prefab bridge structures through the automated fabrication. First part, there was the automated equipment, machine control, and machine guidance, especially for earthwork. And second one is prefabricated bridge structures, and third one is safety-related technologies. And finally, through the digital platform, the public clients want to collect data from every construction project. So this research program is for 6 years. We are now on second years. So I will introduce some outcomes from the first and second year research program. Continuously in Korea, we have new prefab bridge members, including full depth precast decks and the lateral beams, which can adjust the length a bit around 400 or 500 millimeter between girders, because the girder may have some lateral deformation by pre-stressing. And we have precast tunnel arch and also the precast bridge columns. So all the new prefab members are implemented in real bridge construction in Korea. But one thing we lack from those application is the adjustment. I mean the pre-assembly, because they have different suppliers by different companies, and when they deliver their members to the site, the assembler normally have some difficulty. So we need to digitalize the data of geometry change from design dimensions. And also the public clients, recently they have increasing demand of prefabrication for every construction project. It's obviously because of COVID situation. In Korea, there are mostly foreign workers in construction site, but nowadays we cannot have such the foreign workers. So this is the background of this research program. In Korea, in this program, we want to improve current situation on BIM in construction industry. We want to have data-driven communication, because we need to collaborate with other industry, like manufacturing industry or ICT industry. Of course, we need to use our accumulate domain knowledge data. So data engineering model means we like to have data-driven design for manufacturing and assembly, and even for maintenance. In this research program, we are developing smarter prefabricated members. So we need technology on the digital design system, using digital engineering model. And the digital engineering model supports digital fabrication and quality control, and even the member have self-sensing function. So we need to have a digital twin model for lifecycle service. As you see in this slide, we have one algorithm to produce different level of detail digital models, ROD 200, 300, 400. Typically, ROD 200 model can be used for design, conceptual design, and 300 for quantity takeoff, and 400 for fabrication. And the model is dynamic. It means when you have some fabrication error or assembly error, the geometry can be updated automatically by the data. And the digital quality control means that we use scanning technologies to measure the dimensions and locations of connectors, and then the data generated from the scanning, and then the data imported in the algorithm, and we update the original design models. And the model is linked to the performance model. So performance need to be updated continuously because when you have pre-stressing, we have time-dependent behavior. So very simple and low power sensor system is developed, and data from the sensors will update the model performance. So this is a concept of smart prefab members. So if you look at this slide, you can find out how we update every digital model and data from design, fabrication, assembly. And when you update the data, the model follow. I mean, the geometry will be updated together. And finally, we will have an as-built model. So during handover, we will have a digital model and data, and also files. So that is this is digital information delivery through the digital engineering models. So design model, we consider alignments, as you see in this movie. So from the algorithm, we generated design models, and it has a dynamic change of geometry by data from measured dimensions. And it depends on alignment, bridge alignments. So we can generate many different kind of prefab members. So it will be embedded in design system. So model-driven design system is developing now. So as you see here, we have alignments, and the model can be dragged and dropped to the system, and then it fit to the alignments. Of course, engineer may have some adjustment of parameters, and when you finish the design, we can extract data for fabrication. I mean the quantity of concrete reinforcement and pre-stressing steels and some anchorage devices. So this is a design digital engineering model. Digital model-driven engineering is very interesting because we can connect the model to the digital fabrication technologies, 3D printer and robots. As you see in this movie, we started to create very aesthetic design, and then it will be realized by the 3D printing and also the carving by robot arms. So the data will be extracted from the geometry model for fabrication, and we need to add more data for this kind of digital fabrication, like a mixed design, nozzle size, speed of movement, and path. So typically we can describe it as G code. So prefab members, which is fabricated by this process, will have additional data for the digital fabrication. So one of our research team is developing this automated fabrication factory. So among many different equipments, they focus on to develop system mold, distributor, finisher, and curing chamber. And all the equipments import the data from the digital engineering models. And one other, company for the prefab reinforcing bars, they have equipments, and equipments can import data from the digital engineering models. So the data, the flow is automated through the only the data file. We don't provide the geometry models. We only provide the data. Of course, we need after accumulation of data from design, fabrication, and assembly, it will be used for maintenance. And during maintenance period, it is very important to have analysis model, and the model need to be updated from the response of structure. So we developed a very low power sensor system. We considered the periodic inspection period 2 years, and the QR code can visualize the sensor data around 8 sensors by e-paper. Even though we do not have any electricity, the e-paper will be maintained. So we finished the laboratory test, and actually today I visited the site and collected data by drone scanning of QR code, because they erected the girder today, and we will continuously monitor the data to update the analysis model. So I just introduced early phase of our research program. So we found that data-driven engineering communication is very efficient for prefabricated bridge members. Of course, we need agreement how we define the data model and data between suppliers and even assemblers. Through this data engineering model, we can accumulate data, and it can be used for maintenance, and also we can improve the design. Designers will have more data, and they can improve their own design outcomes. And we hopefully have some new service model for digital SoC, including maintenance. Prefab suppliers may have such a new service model. And this research program will have next phase of technology implementation for another 4 years. Thank you for your listening, and hopefully I want to join in the next conference in USA.